Here's sample test problem number 7. A uniform rod, mass 2 kilograms, length 0.6 meters, is free to rotate about a frictionless pivot at one end. The rod is released from rest in the horizontal position. What is the magnitude of the angular acceleration of the rod at the instant it is 60 degrees below the horizontal, and what is the angular speed of the rod at this point? If it goes 60 degrees below the horizontal, it's going to look something like this at that point. And this angle then would be 60 degrees, and the rod would be moving in a circular direction as it's headed downward like that. If we're talking angular acceleration, we should be thinking torques, because we're going to get angular acceleration from torques. And if we're talking angular speed, we should be thinking energy in terms of moment of inertia and that sort of thing. So that's the way we need to approach this. So for the first part, we're going to think torque. We got one force acting on this rod, that is the force of its weight acting on its center of mass in a downward direction, mg, with a moment arm going up like this. If we look at that triangle, which is like this, with a 60-degree angle here, that moment arm will be this distance from the axis of rotation, and that's going to be equal to L divided by 2 times the cosine of 60 degrees. Cosine of 60 is 1/2, so that's going to be L divided by 4. So the moment arm for that weight force of mg is going to be L divided by 4, and that torque is going to be mg times its moment arm, which is mg times L divided by 4. That will be our net torque on the rod. Equivalently, we can say that net torque, if I can get this to right, is equal to the moment of inertia times the angular acceleration. And the moment of inertia of a rod about its end is 1/3 ml squared. These two torques should be equal since there's only one torque causing the net torque. So we should have that our net torque equals our torque, and we have 1/3 ml squared alpha is equal to mg L divided by 4. Get rid of an L on both sides, one of the L's, and an M on both sides. Solve this for alpha, and we have alpha is equal to 3g over 4L, which is going to be 3 times 9.8 over 4 times 0.6, and that is equal to 12.3 radians per second squared. So that is our angular acceleration at that point, and we had to do it using torques. Now, to find the angular speed, we have to use energy, because we can't use rotational kinematics because the angular acceleration is not constant on its way down. The only reason we can use kinematics is if we have a constant acceleration or a constant angular acceleration in this case, and we don't. So we have to use energy. So we have to look at its initial position as being point A, its final position as being point B, where the center of mass is, and we've moved down a height equal to the difference in those two positions, and that height will be equal to L divided by 2 sine 60, and the sine of 60 is 0.866. So this height is going to be equal to 0.433 L, because 0.866 divided by 2. So that's the height that goes down from A to B. So strictly speaking, we have that the potential energy we have at A, which is mg times our height, will equal the kinetic energy of rotation we have at B, which is 1/2 I omega squared. So we have mg, the height is 0.433 L, and that's going to equal 1/2 times the moment of inertia, which is 1/3 ml squared, times the angular velocity squared. Well, an m cancels out on both sides. One of the l's cancels out. And solving for omega, we have g times 0.433 times 2 times 3 equals omega squared. Oh, divide by L here, equals omega squared. Or omega is going to equal all this square root, 9.8 times 0.433 times 2 times 3 over L, which is 0.6, all that square root. And that's equal to 6.51 radians per second. So that is the angular velocity at the point when it's 60 degrees below the horizontal. 6.51 radians per second. This is part B. This was part A. And we had to do it, the last part, by energy because the angular acceleration is not constant. So we had to use energy.